Hi everyone, this is Mrs. Lee. We are on lesson 2 in module 5 of the skinny book. Anyways, it's called Endless Forms Most Beautiful. So you should be there. Again, here it talks about what it's going to be about. So the key characteristics of quadratic functions. Our learning targets, I know it says goals here, but it is targets for us, same thing, is to identify the factored form and general form of an equation for a quadratic function. So far there are two forms, factored and general. I like to say standard, either way is okay. The standard form and factored form. There is a third form, but we're not going to learn that just yet. And then the other one that we're going to do is determine the absolute minimum or absolute maximum point on the graph of the quadratic function and identify this point as the vertex. So remember, we're talking about here the when it's open down or open up, right? So that's going to be that lowest point there, that lowest point either here or the highest point, and that's the absolute minimum or absolute maximum. Remember, you can only have one per parabola. So you can either have a minimum or you can have a maximum. You can't have both. Okay, so it's just one or the other. You can't say, oh, the minimum and the maximum is like, you can't do that. Okay, minimum is this and the maximum is that. No, it's just only one. When we talk about other shapes, other polynomials, then we can have other like two maximums, right? Or three maximums or minimums or whatever it is. But in this case, we just only have the one. All right, this can be found, I'm using period 7 right now under 91720. So just so that you know where to find it, I'm using in the content library. Remember, the collaboration spaces for you guys can collaborate there together. So when you guys are doing breakouts, you'll use that. But we are going to be in the content library. That's just when I'm writing it. Okay, so not to be confused. And so I'm going to make it a little bit bigger. And if you notice right here, so I'm going to just write on here the min. So this is like if you have a minimum. Then if you have a parabola, that's a maximum. Oh, I like this ink. So all the ones that I'm going to write for this video are going to be in this weirdy color, real cool color. Okay, so this is like a min. This is like a max. So min, max. The reason why it says absolute, because there are some graphs, not right now, that are going to look like this, like a mountain, right? So this one would have two maximums. So the highest one would be the absolute maximum, because that's absolutely the highest. This one would be like a relative minimum, not like, it is a relative minimum, because relative to all the other points around it, that's the highest, right? Here it only has one minimum right here. So this one would still be like a relative minimum or a local minimum, same thing, local maximum, right? Although it doesn't have an absolute maximum or minimum because of these lines that go down like to infinity. There is no absolute minimum here. Okay, so there is, that would be for later on, not yet, later on in this quarter. All right, and remember we're gonna call these, it says we're gonna identify this point as the vertex. So this guy, we can call it, so these two guys, in general, we just say these are vertices, not vertexes. We don't say vertexes. One vertex, two vertices, just like how you would for geometry, right? So this is like a quadrilateral. The corner, remember the corner is a vertex, right? So if you have one corner, it's one vertex. Two corners is two vertices, okay? And we're the other learning targets we're going to learn tomorrow. Okay. So here we go. So these are the different words that we're going to be looking at: concave up, concave down, the general form, or I can say right here, standard form. All right, as I slowly write that down. If ever you want to just write this down, make sure that you pause it and then you could write it down and then continue. That is the benefit of having a video. Also, you can go back and remember, like I said, into our class notebook and then into the content library and then still find it that way. Okay. Remember here we talked about the warm-up is the slope-intercept form. The y-intercept is always this number that's by itself, right? The 1. And then this problem is just a random problem that I was explaining something. And then this m is a slope. Think of m is for mountains, and mountains have slopes, right? Is just the number that's in front of x. It's not, the slope is not 3x, it's just 3, okay? That was a common problem that a lot of people had. So here, since we have no number that's there, remember it's just a 0. So the slope is equal to 3, y-intercept is equal to 0. If you were one of those people who did not do this part, make sure you do this, or if you were late, you didn't come to class today, make sure you do this first and then hear the explanations, or else or check your work, because or else it's not going to help you that much. If you really don't understand it, then yes, please listen to it and then try it yourself. Okay, that's the best thing. You need to give yourself time to process. Give your brain a chance. All right, so and this one we had just we just distributed here. So yeah, we distribute the 1/2 times x, which is giving us 1/2 x, and then 1/2 times 5, which would be 5/2. Okay, and the only other thing that I wanted to take note here is just remember that for the y-intercept, right, the b, that's going to be if the sign in front is minus. I remember it could be written as a plus negative, right? So I interchanged the minus and the negative at the same time. It's like the same thing. So if I say negative and you're like, well, that's a minus. And I'm just, in my brain, I'm already making that a plus negative. And then so I interchange them as the same thing. So that's why this is -5/2 instead of a +5/2. So this sign really makes a difference. Okay, like here, it's a +1, that's why it's a +1. All right. Only other thing, okay, there were some things that we had talked about, some key characteristics. So here we have the y-intercept. So if I'm asking you, what are the key characteristics of a parabola? Well, you say, well, the y-intercept, and you would state what the y-intercept is, whatever the function is. And then the x-intercept, which we know as the roots. We learned that last time. And then the min or the max, whichever one it has, right? Whatever the vertex is. Oh, another thing I should note, that the max or the min is we just state as the y value. Y, oh, I should say, oh, that is not that right. So I'm going to say y coordinate of vertex. So it's the y part, because we're looking at this up and down, right? That's talking about the y value. So we're looking at the y coordinate of the vertex. So if we're looking at this one right here, we're looking at how low it is. So that would be talking about our y coordinate, not our x. It doesn't matter about our x. So if you say our minimum is, let's say that's a 2, then you would say minimum equals 2. And that's fine. You don't have to do a coordinate. But for the vertex, you actually need a point. And it needs to be in some kind of point form. Like, so if I'm going to say if this is -2, then I would say vertex is 0, because we don't go up left or right, right? And then this -2 in this case here. Okay, so it has to be in point form. Coordinate notation, I think that's what it's called. I forgot the name of it. Ordered pair form. And then so open up, open down. So that's where we decide which way it is. Remember, we figured that out by looking at the number in front, which we call the leading coefficient. We'll talk more about that in a bit. Okay, remember I drew this little picture here. So if the leading coefficient is positive, then it's gonna make this u, right? It's positive. And if it's negative, it makes it flip it over. It flips it over. Okay, and it just goes down this way because it's negative. All right. So we did a lot of trying to see different patterns and how these equations are connected to these graphs, as well as the tables. And a few things to note. I'm just going to go over this one right here. So a few things that were noticed was this number. Remember, just like the b and for the y equals mx plus b, that b was a y-intercept. That is true for this as well. Because remember, on the y-axis, that's where the x is equal to 0. So literally, if we put 0 in for this x and 0 in for this x, those two are just 0, and 0 plus 5,000 is 5,000. That's why this is always the y-intercept. Okay, so that's why this is y-intercept, and that's 5,000. And yeah, just to verify on the table, yes, at 0, when x equals to 0, y is equal to, or r of x, I should say, is equal to 5,000. Okay, and then just to check, and so that's like if that was something that you notice and you're like, oh wait, let's see if that's really true. I'm trying to think out loud. Then you look at the other one, Punkin Chunkin, and you were like, okay, so this is the one that's by itself, so plus 68. So if we're looking here, it looks like it could be 68, I'm not sure. So, and then you would look at the chart and it would be 0, 68, and we're like, yeah, 68. So that's what it tells you, is the y-intercept right here. The number in front, this is what I was talking about, the leading coefficient. So the leading coefficient is the number that's in front of the variable with the highest exponent. So if this was, this squared was over here instead, then the leading coefficient would be 400, even though it's not in the front. It would not be in standard form, but it would be in front. So like, for example, if I wrote on here 3x plus 5x squared minus 1, the leading coefficient here is 5 because it's in front of the variable that has the highest exponent, okay? And if I say negative 2x plus 3x minus 7x, okay, let me put the, this will be 3, this will be 2, this will be, well, I'll just leave it as 1. All right, and then so what would you say that the leading coefficient is? And you would say, well, where's the highest exponent? And you're like, oh, it's not the 2 anymore, it's the 3. So yep, it would be this negative 7 right here. This negative 7, remember I said I was going to introduce that because that's like a plus negative, right? That's going to be the leading coefficient, okay? So, but we're not going to get to cubics until a little later, right? So for us right now, exponent of 2 is going to be the highest. So that's going to be our leading coefficient, all right? But normally we just write these in standard form where this is the biggest exponent, then the next biggest, then the constant. Okay. Okay, where's me mouse? All right, so that's the leading coefficient. So if the leading coefficient is positive, then just like our smiley face, it's going to open up. All right. And then if it's negative, it's going to open down. In other words, it's going to have a max. Okay. And the third thing that you know from these, just looking at the equations, that if you notice these right here, this is in factored form. So it has these parentheses where like x plus 10 is a factor and x minus 50 is a factor, and then negative 10 is a factor. So I notice right here that if I take the opposite of this number, 10, and that's negative 10, that is the same thing as one of these x-intercepts here. See if that's true for the other one, right? So instead of this minus 50, it's the opposite of that, which would be plus 50, right? Then, yep, sure enough, that's my root, right? So that's my other x-intercept, okay? So these, in the factored form, it will tell you always the roots, okay? And I'll show you how to do that later on, like not today, but we will get into more of the specifics of it later on. This is just more like the overview, the conceptual, like the vocabulary, right? So those are the roots. All right, and how can you tell from the structure that the equation is quadratic? It's got to have a 2. It's got to have that square on there, okay? And if you're looking for an actual like square, okay, you won't find one because it's this kind of square, okay? But where does that come from? Since it's a video, I can show you. If you don't want to know, just fast forward. The reason why it's called a square is because, okay, so if we have 1 dimensions, oh, let me go back. We'll go into my college stuff. Oh, shoot. Okay. Now, if we have 1 dimension, right, it's just 1 dimension, 1 direction, right? Left, right, that's all we got. So that's going to be our linear, right? Our left and right. Now, if we go 90 degrees from that, now we're in 2 dimensions, right? So 2 dimensions, it goes this way. And then we have, so if this is 1 and this is 1, then this area right here is 1 square, right? Remember in geometry, we learned about, well, in elementary school too, you learned that a square has all 4 equal sides, right? So remember we said that we're going to draw this at a 90-degree angle. So this must be a square. So that's why we call it 1 square foot. Like when you're looking at square footages of apartments over homes, right? You want to see how big something is, like your room is or your house is or whatever. They're looking for square footage, right? And the reason why they call it, they're like, how many 1 by 1 square tiles, if you were to put them down, lay them down on your floor, side by side, how many of those would fit in there? That's what 1 square foot comes from. Okay, so that's why it's called square, because that's 2 dimensions, square, right? Which means just as an extension, right? If we were to go 90 degrees from a flat flat surface, right? It would come out this way, right? We would have the third dimension, right? So we are three-dimensional people, right? So we can't really draw that here very well. Some of you guys can draw way better than I can, but I'm gonna just do my attempt. So we're gonna go back this way. So make it about the same distance every single time. Then you can make it look like, so remember this is also 90 degrees. Now we have a cube. That's why, so when we're gonna go one back, so this is one exactly the same distance, right? So now we're gonna have one cubed. That's why we call it a cube, because guess what? It's a cube, like a sugar cube, right? It has the exact same dimensions, 1 by 1 by 1, or x by x by x, or 3 by 3 by 3, right? That's what we call this x to the third power. That's what we call it x cubed, because we just cubed it, right? So, oh, I'm gonna say x. I was gonna try and see if I can, oh, I can do it. There we go. So x times x times x, this is x cubed, okay? So if you take ice and you multiply it with 3 times, ice times ice times ice, ice cubed. All right, I'm just kidding. All right, anyways, so that's where that whole, that's why we call it a square and a cube, just so that you know. Just some little tidbits. And so this is basically the gist that I wanted to talk to you guys about. First differences and second differences. Okay, whenever you have a table, a couple of different things. May not have mentioned it in maybe your class, I don't know. But remember that the x's have to be in order, and usually they are going by ones. Sometimes they'll go by twos, depending. But it's always the same increment, okay? And then for this one, for the ones on the right here, then they're just gonna follow. So it's just the x's are always gonna be in that, from lowest to highest. Okay, it's always gonna be in that order. All right, so notice right here, remember f of x is the same thing as y. And when we take the first difference, that assumes that there's a second difference, right? Like if you have a, like if you have first place, then you assume that you have a second place, right? Same thing, or in third place. So same thing here. So what we're gonna do is we're gonna take the bigger number for the x. So we're gonna take the 4, and we subtract it by the 9. So it's gonna be 4 minus 9, which is 5, negative 5. So we're trying to find the difference. How far is the second y with the first y, right? So how far is that? And so that's gonna be, it's negative 5. Okay, remember we're talking about direction as well. And then so from 1 to 4, where are we going? If you're at, another way to explain is if you're on the number line, right? So so if we're at 1 and you're taking away 4, where do you end up? Oh, I'm gonna go, here's 1, and then you can go 1, 2, 3, 4. So where are you gonna be at? Of 3. Okay, so we're going actually to the left. So minus 4. Okay, so that's another way to think about it if you're not good with negatives. All right, so again, these are called first differences. And if you notice right here, is that these first differences, negative 3 minus, oh shoot, first differences, sorry. I got confused with my writing, right? So we see here negative 5, negative 3, negative 1, 1, 3, 5. What do we notice? There are some repeat numbers, right? They're like opposite numbers. There's like 1 and negative 1, 3 and negative 3, 5 and negative 5. There's a pattern there, but I'm not exactly sure what that's going to tell us yet. So let's try the second difference. So this right here is the second difference. So I should label that here. So this is second difference. Okay, and so when we do that, we're going to take the difference of the differences. Okay, so we're going to take negative 3 minus a negative 5, right? Negative 3 minus a negative 5. If you need a little diagram of that. So if we're at negative 3 and we're going to take away, which means go left, like, right, because we get smaller. But what are we going to do? We're going to take away a negative 5, which means negative means go the opposite way. So we're actually adding, okay? So we're going 1, 2, 3, 4, 5. So we're actually going more positive now because we're taking away negatives. So that'd be 2, 3, no, negative 2, negative 1, 0, here 0, and then 1, and then 2. So it would actually be here. So Here's -3, and take away a negative. I don't know how, you know what I mean. Okay. And if you want to use your calculators, just make sure you use the right signs. And then you put this double, like this double, the minus and then the negative sign, because in your calculators usually will consider that to be different. Although I think on the calculator phones, I don't think they do. Anyways, depending on what calculator, I suppose. And what do you notice? They're all 2s. Okay, and if they're all, these are all 2s. I just didn't show my work here, right? And so you'll notice for all quadratics, all second differences will be the same number. So this one is going to be all 2s. There might be some that are all 3s or all 2.5s, right? But it's all going to end up being the same difference for the second difference, okay? So the first difference for quadratics will be different, but they should be, you should see some kind of pattern going on if it's close to the vertex. And then, because remember, it does one of these things, right? Or these. And then the second difference should be the same. All right, and so that's, and if you, this is, I would underline this, this is like the definition of second differences. So, and we already did that, but you notice they're all the same. All right, so I'm gonna kind of skip over this part because you could, please read it, try reading it, right? For me, it was a little weird. I was like, I don't know if I like this way, and it was hard for me to explain. So, but this explains the first differences and the second differences. All right, moving on. So now we're here. So remember, we're going to be identical. So we look at this and we're like, okay, this definitely doesn't have a 2 there. Well, it has a 2 in front, but that has a 5. Right? And so we know this is linear, right? So we wrote down linear, and we're going to find the first differences. So we're like taking the -4 minus the -6. If you want to do these little things and put them in, it seems to help me sometimes. So -4 minus a -6, which is 2, right? Remember, minus a negative, same thing as a plus. So that's gonna, and I noticed 2, 2, 2, 2. So it looks like for linear, they're all gonna be the same, because, you know, which makes sense, because remember, it's constant slope. The rate of change is constant, so it's going up the exact same amount every single time from point to point. So anywhere you pick on the line, if you take that point, you go up to and to the right one, you're still gonna get there, right? So if on this point I go like right here, and I go up to, I'm trying to do a dotted line, it's not working very well. And then to the right one, oh look, still on the line, magic, right? You don't even have to start at a little, like a nice point like that. As long as, if it's the same distance, unit-wise, 2 units up, 1 unit across, 1 unit to the right, you will land on the line. If you go 3 units up, 1 across, you're not gonna land on this line anyways, right? Because this slope, which talks about the rate of change, so this is like the rate of change, if you want to think about it that way, since our x is just 1, the differences are just 1. Yeah, you're gonna see that one. All right, so again, our second differences then for linear would all be 0, because there should be no different here. There should be no differences here. So they should all be the same number. And so this one we know is a quadratic, not because of the coefficient, right? But because of the exponent, the little number right there. Okay, so that's why we know it's quadratic. And we're going to, again, do the first differences, and you notice -10, -6, -2, 2, 6, 10, right? And second differences, if you subtract all of them, it's going to be 4 all the way down. Okay, and this is what your picture should look something like. All right, and this is what I asked you guys to finish. If you have not finished it yet, go get your book and do it now. Pause. But if you haven't, we've already done it, then this is a good time to check. So this again is going to be linear because there is no exponent here. That if there's no exponent, we just automatically assume it's a 1, because x to the 1 power is just x. Like 5 to the 1 power, that's 5. Because how many times are we multiplying by 5? Just once. So 5 multiplied once is just 5. 2 to the 1 power, 2. 5 to the, anyways. Okay, so here again, the first differences, I'm not going to write down the work. I'm just going to write down the answer once I can get to that page, is going to be -1. And if you did not get -1 and you think I'm wrong, which is very possible, I've had mistakes before, I too am human, then please tell me. Again, I can make that correction. And again, the second differences are all going to be 0. All right? And then if we're going to graph them, it is going to look like -3, 7, boom, right about here. Notice, if you notice the slope, It's like 1 down, 1 to the left, or 1 to the right. That's the slope of -1. That slope is negative. This slope is negative. This is negative. Coincidence? Did you say, I think not? I said that too. I think not. Okay, I'm going to change to a different color just to, let's see if I can do this right. Okay, please use a straight edge. I have like a board. So it's, oh, that's not bad. Okay, so I have one of these guys, so it's not as easy for me. I can't just use a ruler. All right, and then for the second one, this one is, you should have gotten, this is definitely quadratic because it has this exponent of 2. All right, and we have first differences are, okay, we got 5, 3, 1, -1, 3, oh, -3, -5. All right, and the second differences we got was, and I would recommend that you write this out. This is just for answers, okay? So you would go 3 minus 5, which would be -2. That's how I'm getting this. 1 minus 3, which is -2. If you do it in your brain, do it in your brain. All the more power to you, right? If you're getting like -2, 2, and then you're like, oh, shoot, check your work, okay? Because we know that for quadratic, second differences are the same. All right, so we're going to plot this, dudes. All right, so we got -3, -5 right here. And then we got -2, 0. Ooh, that looks like it's an x-intercept, i.e. root. -1, 3. And 1, 0, 4. 1, 3. Oh, I know it's symmetric. So remember, if it's symmetric, that means the left-hand side is equal to the right-hand side. So it looks a little bit easy. All right. I'm gonna try and see if I can do it with something thinner. So remember, we shouldn't be going all the way out here because we know that the next number, we're not gonna be able to graph that. So we're gonna go. Oh, this is, oh, shoot. Okay, you know what? I'm gonna try that one more time. That was terrible. Okay, you do a much better job than I can, please. Let's do it slow. And all those people who draw out there, I know you can do a very good job of this. Oh, shoot. Okay, but yes. Hopefully you did a better one than mine. Okay, so yeah, so that's going to be your parabola. All right, so that's what you should have gotten for that. And then what is the thing? Okay, one thing to notice that for second differences, remember, so you notice the second difference is negative, which means that this is also going to be negative. That's another thing that you can see. You don't really need to know that. I mean, it's just nice to know. It's just good to see. But if you have second differences, that means, you know, you probably have these points, you know. But if someone were to say, if your second differences were positive, is it going to open up or down? And you'd be like, ooh, positive, open up, right? Or concave up. All right. So, and if your second differences are negative, then it's down. Okay. Oh, and also another way to word that, instead of saying open up, open down, they also use concave up and concave down. So if you guys are nearsighted and have glasses, right, if you look at your glasses, they're like shaped like this if you're nearsighted, right, because it needs to be concave. It needs to be concave. Concave meaning it's like a cave. I think of it like a cave. Convex is the other one where it's not a cave. It's like it comes out like this, right? So anyways, so this is concave, right? So concave up, so the cave is up or cave is down. So concave. Okay, anyways, so we're gonna go on to analyze the leading coefficient. Remember, we talked about the leading coefficient. There were 2 forms that we talked about in the learning targets. One of them was the general form, or like I like to call the standard form. Remember, it is f of x equals, I don't know why that's not really clear there. I'm gonna just write that equal sign there. On your books, you should be able to see it. Oh, that's just a straight line. So equals ax squared plus bx plus c. that's something that you need to know. You need to remember that, okay? And when I refer to A or B or C, I'm referring to those in this context, okay? Usually we won't talk about B because B is not that interesting, but it's usually either the C that I'm talking about or the B or the A that I'm talking about. And this A is the exact same A as this A right here. They are the same number, okay? So if this A was going to be like 5, then this A would also be 5 if we're talking about the same equation, just in a different form, okay? So that A doesn't actually change forms. That A is going to be the same either way. But the other stuff in there is going to change, okay? So also this is where A is not equal to 0, because of course if A was equal to 0, the x squared would be 0 as well, which, because, you know, 0 times anything is 0. So that's why A needs to be something other than 0, because then we're just stuck with a linear problem. All right, and remember it says C is a constant, and remember it's our y-intercept. So factored form. So A, again, is here in the front, and then this is in factored form. We'll talk more about how to factor, like how would you get it from standard form to factored form? Like how do you do that? We're going to talk more about those things a little bit later. This is just to get an idea of it. And why do they call it R1 and R2? Remember what they told you? I would like to scroll back up, but just you couldn't do it in your books. Remember I told you the roots, right? So remember it was always the opposite of what we were seeing in there. I would say, well, what's the opposite of like 10? And it was -10. The -10 was a root, I think, for that ghost tour or something like that. So these are the reason why we had to do that was because these are originally, the form is originally minus. So it's always going to be the opposite of whatever you're seeing. I always think opposite of what I see. Okay. So there is a different way to find that. I will show you that, not today, but in the future, I'll show you how to do that algebraically, because it'll get a little more complicated. So anyways, you're going to go back and identify the general form and factored form of each equation in the getting started. Okay, I'm going to actually have to scroll back. All right, so we're going to scroll back. Sorry, you can close your eyes if you want to. Okay, here we go. So here, standard form or factored form. If you notice, I'm noticing right here that I see an s squared. So if I see that square and all the variables are in descending order, so we have s squared, then just a regular s, and then our constant number, then that's going to be in standard form. So this first one is standard form. I see here parentheses and like variables in the inside of the parentheses. That's my factored form. All right. So the first one here for the handshake problem, standard form. Second one, factored form. It's so difficult. This one right here, standard form. Second one, factored form. This one, you want to say standard form, but it's like, what? Wait, they have parentheses, right? They have parentheses and they have variables inside. Not necessarily have to have the numbers, but usually you do. Then that would be factored form. And the second one here is standard form. So don't get juked. All right, so I'm going to scroll back down again. Sorry, close your eyes if this hurts your eyes. It hurts my eyes. I can't close my eyes. All right, so remember, what does the leading coefficient tell you about the graph of each function? Remember the leading coefficient, we are calling that what letter? We're calling that the letter A, right? Going back to this A right here. Actually, we wouldn't call that the leading coefficient. It's just, yeah, it's the number outside of the, anyways. We're referring to this guy right here in a standard form, but these numbers are the same. That's why they kept that as an A, just so that you know. All right, so so the leading coefficient tells you if it's positive, then it's going to be open up like that, right? So I don't know. And if it's negative, then it's going to be open down. Okay, just like the smiley face and the sad face thing, right? Oh, there's the 2 pluses. Remember, just like my calculus teacher told me. I really like that one. That's the one thing I remember from high school. Maybe you'll remember this from high school too. And you'll say, my Algebra 2 teacher taught me that. And then you could teach your kids that too. How does the leading coefficient relate to the absolute minimum or absolute maximum of each function? Well, obviously, if he tells you which way it's opened, right, then it's going to tell you that, right? So if it's this way, I'm just going to write it here. So this one would give you the minimum, right? And this one would give you the maximum. Okay, that's the maximum. All right. You can write those in your words. You're good at that. I'm not good at that. So how can you determine the y-intercept of the graph using the general form, i.e. standard form? Do you remember what letter that was? Remember we talked about? Yep, it's this plus c right here, okay? So this is gonna be, the c is gonna tell us that, okay? Yeah, so look at the c, look at the number that's by itself, okay? That's gonna tell you. And here, yep, this is good. The graph of a quadratic function has either an absolute maximum or an absolute minimum, not both. And then determine from the equation whether each quadratic function has an absolute maximum or an absolute minimum. Again, like I said, for us, we all know in quadratics, parabolas only have either one max or one min. So if you don't say absolute, I'm absolutely okay with that. Well, for the other, when we go into polynomials, we'll have to make that distinction. Okay, so here we're looking at, remember the a, which is 2. So I should say equals. So we know that it's positive because there's no negative there. So I would just draw a picture there, and we know it opens up, i.e. concave up. And then so a is equal to is positive, right? And that's how we know that opens up, all right? And so this one right here is negative. So here is negative. So this is gonna be sad face. So it's going to be concave down. I'm going to try and use the word concave down. All right, and because I'm going to say BEC, that's my shorthand. Some people go B/C. I can't get used to that. I made this one up in college because I'm like, I can't write that fast. Because A is equal to -2. All right, and right here, again, I'm just going to do it quickly. So this is going to be concave. Oh, and if you did not do this already, you better pause this and then do it and then check, okay? Because don't just mindlessly watch this for no reason. Oh, okay, some reason, but still, you got to process this. Concave down because a is equal to -1/2. This one is going to be, oh, this is in factored form, but still a is still this right here. So concave down because a is equal to -0.0009. It's barely negative, but it's still negative. All right, and then we're gonna go, this is gonna be concave up because a is equal to 1/3. Oh, that's 1/3. And this is gonna be concave down because a is equal to 2. Did you guys say, wait a minute, Miss Leanne made a mistake? I think that's wrong. I hope so, because if you were copying down concave down, then you'd be wrong, right? Is this really concave down? No, because this is positive. If it's positive, then it should be concave up, happy face, right? So good job. If you caught that, you were like, good job. I'm very proud of you. Okay, so concave, this should be concave up. Perfect. See, I told you I make mistakes on purpose sometimes not on purpose, but you know. All right, and then your assignment here was gonna be, or is, this guy and this guy. All right, so please make sure you check those answers in the homework reflection thing on Canvas. It'll give you the answers, not give you the answers, well, it gives you answers, but it's so that you can check. Okay, and sometimes those answers are wrong, so make sure you verify that with me. If you feel like you're really right and that answer is wrong, then the book's wrong. Then just tell me, because we already found one mistake in one of the problems that I already made a correction on that. So make sure you tell me. All right, and yeah, if you need a review on any of these parts, go back, rewind, do all that kind of stuff, okay? I'll talk to you later. Bye.